So we're going to have a look at, we got to the end of, or the sort of did a little bit of empirical formula, a molecular formula today, guys. In our end of class, we got cut off, unfortunately, with that 40-minute limit. So what I've done here, I'm just going to do a few empirical formula, molecular formula for you. I'd appreciate it if you would have a look through them. Okay, and then we'll just do a few examples. These shouldn't be too difficult. They're a little bit more tricky than some of the ones perhaps you did at GCSE, but it's just the wording of the question. So the more you do, the more familiar you become with the wording of the question. Okay, and then hopefully the easier they become. I mean, they're obviously going to be a bit more challenging than GCSE, as you would expect. So I did a couple in class today. We did get cut off quite abruptly, so I'll do them again. I'll do another couple, and then I'll set you guys a few to do for homework. So if we can just remember, first of all, what our empirical formula is. So it's very simply, it's the simplest, and it's important. It's the whole number ratio, okay, of x to y in a formula. So if I have x, y, a compound made up of x and y, it's the simplest whole number ratio. And then if we can just remember our molecular formula, that is the actual number of moles, of x to y in a formula. So let's say I had x to y was the simplest whole number ratio, and I carried out my analysis on this compound, found that x to y was the empirical formula. The molecular formula might be something like x8y4, but the simplest whole number ratio obviously is 2 to 1 there, and that's what we would write from that perspective. Okay, right. So we'll work through a few of these here, and hopefully I'll point out a couple of the pitfalls that you might come across at AS level compared to GCSE level. Okay, hopefully these will be pretty straightforward. So we'll do the two that we did in class today. Right, so we're asked here about a compound which is made up of phosphorus and sulfur. We're told that we've got 4.4 grams of the entire thing. So that's the whole thing together, remember? Some people think that's either the phosphorus or the sulfur. It's not. And we've obviously therefore got 2.48 grams of the phosphorus. So within the compound then we've obviously the 4.4 minus the 2.48. That'll tell us the amount of sulfur that we've got within that compound. So it's 4.4 minus 2.48. So that means that we end up with 1.92 grams of that. Now remember what I said earlier, our P to S ratio here, really what we're talking about are the number of moles of phosphorus to the number of moles of sulfur. So we've got to get moles, and that we've got to then go back to our good old faithful mass equals number of moles times the RFM. Okay, so we've got to get the number of moles of these two. So sulfur has an atomic mass of 32. Take my 1.92 and I'm going to divide that by 32. It gives me a ratio of 0.06, and I divide this by 31, gives me a ratio of 0.08, and then we've got to convert these or scale these up to our nearest whole number ratio. So all we're really, I mean, I would just scale those up to 8 to 6 ratio, if you like. Okay, and that gives us a 4. The simplest whole number ratio therefore is 4 to 3. The 4 refers to the phosphorus, the 3 to the sulfur. So our answer for that particular one then would of course be D. Okay, P4S3. Right, so that I think that's too bad. You probably get one pretty similar to that at GCSE, to be quite honest with you. Okay, the second one, it was the one that I got cut off today, which is a bit disappointing because lots of people were somehow getting it wrong. Okay, so let's have a look at it. So hydrogen fluoride reacts with metal chlorides to give metal fluorides. Determine the empirical formula of tungsten fluoride, right? So the first sentence in that really is pretty irrelevant. We don't particularly need to use anything from it at all. So we've got tungsten fluoride, okay, so we've got to go to our periodic table and we've got to find our tungsten. Okay, so it's in a bit of an obscure place in the periodic table for AS and GCSE chemistry, and it's 184. Okay, it's a transition metal in the third row down in the transition metals. And then we've got fluorine, okay, which is 19. And it's F. What I thought maybe some people maybe were doing today, I'm not sure, because we got cut off, was maybe they were using F2. But remember, it's not. It's made up of the fluoride. It's just the F. So we're working out how many moles of atoms of fluorine there are, not molecules of fluorine. All right. So we simply take we're taking our 6.1 and dividing it by that, and that's going to give us the moles of tungsten that we have. So 6.1 over the 184 gives us a ratio there of 0.0335152, and I wouldn't round these up too much, guys, for the simple reason that sometimes you're working in very, very small numbers, okay, and the more rounding up actually can introduce quite a significant amount of error into it, and then actually you get the wrong answer. So our fluorine, we've got 3.8. Fluorine has an atomic mass of 19. Okay, so that gives us 0.2. So I needed to, like we did when we were doing empirical formulas at GCSE, we take the smallest number and we divide it into all of them. Well, if I take the smallest number and divide it into the smallest number, that is of course going to give me 1. And if I take that, okay, and divide that into it, okay, so okay, that gives me, exactly, so that divided by 0.03315, yada yada yada, gives me a 6. So there we go, that works out very nice. That was the right answer. Quite a few people got that wrong. Didn't get time, unfortunately, in class to delve into why you got it wrong. But anyway, there we go. That's the answer. That's how you get it. Okay, so we'll do another couple of these. Hopefully just until really I'm kind of satisfied that I think I've done enough to kind of cover all bases here. Okay, so let me just get rid of this. Okay, let's go down to here. Right, so this is a bit of a tricky one. We need to be a little bit careful here because it says first of all that we've got 0.2 moles of the hydrocarbon. Now really what we want is what is the mass in one particular mole, but okay, we'll have a look at what they're asking us here first of all. So they're asking us the molecular formula here, and if you remember the molecular formula, that is the genuine number of atoms within 1 mole or 1 molecule of this thing. So remember, what you're going to get here is only going to represent, it'll represent the ratio, but it'll only represent the ratio of 0.5 of a mole. Now there's a couple of different ways to do this. What I would do is I would multiply that by 5, and I would multiply that by 5, and that's going to give me the mass of carbon and hydrogen that are actually in 1 mole of this thing. So 4.8 times 5. Okay, it would give me carbon. I will have 24. Okay, and then the 0.8 times 5 is 4, isn't it? 4.0. Okay, now so this looks kind of like an empirical stroke molecular formula question here, but in actual fact, if I do it that way there, okay, I get that this RFM here has to be 28. So I can go over here and check if any of these are 28. Well, that's not 28, that's not 28, that's not 28. So there you go. B is actually your answer without me having to do any of the type of working out that you would normally associate with an empirical molecular formula. Right, okay, so let's look at the next one. We've got magnesium and we've got nitrogen. Again, remember this is nitrogen atoms that we're talking about, not nitrogen N2, which you're very used to talking about. Okay, so in the compound, the nitrogen is as a nitrogen atom, not as a nitrogen molecule. All right, so we've got 7.2 grams. Student burns 7.2 grams magnesium and nitrogen and finds that 10 grams of the magnesium nitrite. So really the only thing that might trip you up here is working out what mass of what mass of nitrogen there is in there. So if we do 7.2 divided by the 24, that gives us, so if we do that over the 24, that gives us 0.3 moles of nitrogen. And if we do our 2.8 divided by the 14, not by the 28, okay, that gives us 0.2 of that. Then we're looking for the formula of this thing. So our ratio of magnesium is 3 down to 2, or 0.3 to 0.2, either way it's 3 to 2. So our answer has to be C. Now you could in actual fact go onto the periodic table and worked out that magnesium was 2 plus and nitride was 3 minus, done the crossover arrows and got that. That is not a good way to do it, because very often they will change around what it actually is in the periodic table. So please don't go down that route. Okay, use the values, use the numbers that are on the in the question. Okay, next one then. So we have 8.2 grams of an oxide of chlorine. So this is chlorine with oxygen. Okay, we have 8.2 grams. It contains 8.2 in total, of which 3.5 grams of that is chlorine. So 3.5 grams of it is the chlorine. So just okay. And if we remember that chlorine has an RFM of 5.5, so that comes out at 0.1, maybe a little more than 0.1. We'll come back to that if this doesn't work out nicely here. We need to get the mass of our oxygen that's in there, so that's our 8.2 minus the 3.5 is the mass of oxygen, which is 4.7, and the moles of that will be 4.7 over 16, which comes out at 0.3, sorry, over 16 comes out at 0.3. So this is alright, this comes out at a ratio that's fine. So we have a Cl, okay, a 1 to 3 ratio. So we go over to our answer and see which one is in the 1 to 3 ratio. Well, the only one that's in a 1 to 3 ratio is our 2 to 6, C. Okay, so our answer therefore must be C in that particular instance. Okay, right, I'll do this one here, and then I'm not going to do part II of this, because part II of this is a really difficult question. I'll be quite honest with you, I'm not sure. I don't think I've ever had an AS chemistry student get part II right. So if anybody is able to get it right, I'll be pretty impressed with them for the next class. But I'll do part I, which is using percentages. Now, percentages we really don't make any difference. All we'll do then when we get a percentage is we'll assume that we have 100 grams of this thing, okay, and that the carbon therefore makes up 18.9 grams of that. So the moles of it will be 18.9 over 12. The chlorine makes up of that 100 gram sample 55.9. So divided by 35.5, and our oxygen makes up 25.2. And that's divided by 16. Remember, it's oxygen atoms, not molecules of oxygen O2, so don't divide by 32, guys. Alright, so we have 1.575, so that's immediately a nasty number. If I'm a student looking at that, I'm thinking, that's a bit annoying. Okay, so 55.9, and the second one divided by 35.5. That gives me 1. Well, my eyes are lighting up a little bit there because those two are the same, so that makes life a little bit nicer for me there. Okay, oh well, here we go. And the final one is also 1.575, so that's perfect. Okay, that makes life very easy. My empirical formula is 1 to 1 to 1, so I just write CCLO. Okay, right, you can have a think of that there, about that. That's a pretty difficult question, okay, but I'm not going to spoil the fun for you. I'll just have a go through here and see if there's any in here. That's that same question again. If there's any in here that are worth my while doing. No, I think I'll leave the rest up to you guys, because they represent a reasonable challenge. I've done some simple ones, I've done some middle ones, and I've done a tricky one there. So I think it's up to you to have a go at the rest of those. Alright, all the best, and I will see you in class next day.